So hello everyone, welcome you all to live session 8 of NPTEL course Fluid Flow Operations taught by Professor Shubhrita Kumar Majumdar, and my name is Nagpan Sai Kumar. I'm the teaching assistant for this course. So last week we have discussed about that is in week 7 we have discussed about flow in water channels, in which we discussed about flow velocity and also optimum shape for a flow channel, and then we also discussed about equations for energy and discharge in a water channel. So this week we'll be learning about, or we'll be discussing about drag and lift along with cavitation as well. So first let's discuss drag and then we'll go to cavitation and subsequently to cavitation. So when does the body experience drag? So whenever there is flow around the body, you will be experiencing drag, right? Whenever the body will be experiencing the drag, right? So let's consider a body, in this case sphere, in a uniform flow. So whenever a body is placed in a uniform flow, so it will always be developing a thin layer along the body surface with largely changing velocity. And this is because of the boundary layer due to the viscosity of the fluid. Okay. So whenever there is a uniform flow around this body, because of this obstruction, there will be a change in velocity. So this disturbance will subsequently be passed over to the other layers as well. So this creates flow suppression, and this is because of the eddies or the turbulence which is formed behind the body, right? So this is when a sphere is placed in a fluid. Let's also see how the flow happens when a cylinder or a flat plate is placed in a flow stream. So let's take the cross section of the cylinder. So let's say this is the cross section of the cylinder, and we also have a flat plate which is placed in the cross section, which is placed along the flow stream. So how do you think the flow will be behaving? So same thing happens in case of cylinder. So you'll be passing over the body, and there will be eddies which are being formed here. There will be some disturbance forming behind the body, and the layers which are very far from the body, they'll also be disturbed because of this eddies that are being formed. Okay, the flow from the upstream point, let's say this is point A, and let's say this point, and the pressure at this point, let's say this is P infinity. Which means this point is sufficiently far away from the body. Okay, so that is why let's denote it as P infinity. And let's say we have a point which is very close to the body, and this is B, and let's say this the pressure is P naught at this location. Okay, so the flow stream, the flow or the fluid which is coming from upstream point, it is A, it will be stopped at point B. Okay, or its velocity comes to zero, or its velocity becomes zero. So this point B, where the velocity of the fluid becomes zero, this is called stagnation point. Okay, this is called stagnation point. Okay, so from point B, so there will be two zones that are being formed. Okay, so one, the fluid will be splitting into two sections. The first section is which will be flowing on the upper surface of the body, so it will be splitting and it will be going to the upper part, and there will be other section that is from the lower part. Okay, so for a cylinder, the flow separates at this location, that is point C. Okay, so from A, the flow will be coming, like let's say this is at infinite distance. Uh, infinite distance is that mean indicates that there is no influence of body at this location. Okay, so that indicates infinite location. It doesn't have to be at actually infinite distance. So we'll select a location such that there will be no influence of the body at that point. Okay, so let's say the fluid is coming from that point, that is A, and upon reaching point B, the fluid velocity will be decreasing to zero, and this is called stagnation point. And there, the fluid will be separating into two parts, that is the upper part and the lower part, and then there will be separation of these two layers at point C, and this is because of the eddies that are being formed in this location. Okay, but whereas coming to the second case, this over a flat plate, so the disturbances that are being formed are like, minimal because of the flat surface of the plate. Okay, so there will be minimal disturbance, and we can also say that there will be no separation as well. Okay, so let's say this is point A, and let's say pressure is P infinity, and we have uniform velocity U. So this is also having uniform velocity U. This is point B, and this is point P naught. Okay. So in case of a flat plate, the disturbances that are being caused are like a minimal because of the flat nature of the, because there will be minimum obstruction to the flow, right? So there will be minimum change in the velocity, and also the turbulence will be lower in case of flat plate. So that is why there will be no suppression of the flow as well. So let's consider the same example of cylinder and flat plate, and this is point C, this is point B. Some eddies are being formed here, or you can also start turbulence. And in case of flat plate, we don't have any disturbance, right? So let's say that the pressure at the upstream, that is at point at the location A. Let's say the pressure is P infinity, and this is not influenced or this is not affected by the presence of body, cylinder or flat plate. And let's say the U is the uniform velocity, of the fluid or liquid, and the pressure at stagnation point is denoted by P naught, right? So this pressure can be calculated using this equation. P naught is equal to P infinity plus rho U square by 2. So that's the equation. So how do you get this equation? We just have to apply Bernoulli's equation. So let's say we have 2 points. This is first point and second point. At this point, P infinity is the pressure, and here P naught is the pressure. Okay. So what is Bernoulli's equation? This is a Bernoulli's equation, right? At two different locations. So these 2 points are at the same location, right, or at the same height. So there won't be any. So H1 will be equal to H2. So there won't be any potential difference. And also at location B, so let us indicate it as A and this as B. Okay. And at location B, velocity is decreasing to zero, right? So ub will be zero. So this will also become zero, and we'll be left with pb is equal to pa plus half u square. Sorry, this is rho. Okay, so we'll be left with rho by 2 u square. Okay, so what is the pressure at pb? So we were denoting it as p naught, right? And at pa we were denoting it as p infinity. So this becomes u square. So this is what we got in the first equation, right? So this is how you can calculate the pressure at stagnation point using Bernoulli's equation. So a body realizes a force from surrounding fluid whenever it is placed in a flow of fluid. Okay, so that will happen every time whenever a body is placed in a fluid. It will always be experiencing this force like from the surrounding fluid. Okay, so a flat plate realizes a force only when the downstream direction. Let me first draw the diagram. Let's say his U, the resultant force. Okay, so a flat plate realizes a force only in the downstream direction when it is placed in the flow direction. Okay, so however, in case of a wing, so in this example, so in case of this wing, so this realizes a force R inclined to the flow as shown in the figure. So there will always be lift and also drag as well in case of a wing. So this is because of the resultant of two forces. One is the drag force which is acting in the direction of flow, and then the other force, that is L, which is acting in the perpendicular direction. This is called lift force. Okay, so the resultant will be R, which will be also be in the direction of flow. Okay, so in general, R force acting on a body can be resolved in two components. So this R can be resolved into two components, that is L and D. Okay, so D is the drag force which is in the direction of flow, and L is the normal force or lift force which is in perpendicular to the force, perpendicular to the flow. Okay, R is the resultant force which is experienced by the body. So one is in the direction of flow. So this is also called as drag force, and the other one is component L in the direction normal to the flow, and this is referred as lift force. Okay. So let's consider pressure of a fluid acting on a given minute area. So let's consider a small area that is dA at this location. Let's say the area of this surface is dA. Okay, and the pressure acting on this body, let's say P is the pressure acting on this body surface. So first there has to be flow rate. Let me draw it. So this is U, that is uniform velocity. Okay. So dA is the surface area of this small element that we are considering, or body that we are considering. Okay. So here, because of the flow, there will be a certain force that is being exerted here, right? Because of the flow. So let's say this is P, it is pressure into dA, that is the surface area. Okay. And let's say, so here P is the pressure of fluid acting on minute area dA on the body. And let's say tau is the friction force per unit area. Okay. So now pressure P into dA, that is, sorry, the force that is P into dA, which is caused by the flow of the stream. It will be normal to the surface, right? So this is 90 degrees. Okay. So this will be normal to the force, sorry, normal to the surface. If this is the surface, there is a small element. So this will be perpendicular to the surface. And also, we have one more force that is frictional force. This will be acting tangentially to the surface of the body. So this should be acting in this direction, is tau into dA. Okay. And the resultant force will be in this direction. So let's say this is theta. Okay. So the drag force dP, which is integrated over the whole body, whole body surface of a component direction of flow is U, will give us foam drag or pressure drag. Drag dP is the integration of over the whole body in the direction of flow, or flow velocity U is called, or pressure drag. Okay. And we also have one more force, that is DF. That is because of the frictional force. So this is again similar integration of T into dA, and it is called friction drag. So we have to integrate over the entire body. So if you just write this in mathematical terms, dP will be over the integral over integral P dA cos theta over the entire body, and dF will be integral T dA tau dA sin theta over the entire body. Okay, so basically dP, that is pressure drag, is the sum of pressure drag acting on the body, and dF, that is frictional drag, is proportional. Sorry, friction drag will be varying with the shape of the body, because when the body shape changes, tau will also sorry, the drag D on the body is the sum of pressure drag dP and the friction drag dF. Okay, so D will be dP plus dF, which whose proportions vary with the shape of the body. Okay, so let's see how the percentage of dP and dF varies, or the contributions of dP and dF varies with the shape of body. So this is the total drag will be sum of dP plus dF, but the contributions will be changing according to the shape of the body. Okay, so let's see how it changes. So let's take a flat plate where the disturbance is minimal. This is U, and this is point A, and this is point B. Okay, so everything remains the same. So in this case, this is dP, and in terms of percentage, how much does dP and dF contribute to the total drag, is D. So in this case, dP is zero. The drag due to pressure drop is zero, and because of friction, it will be 100%. And if the body is in this shape, that is having a flat surface in the field, and then having a shape something like this. So in this case, drag due to pressure will be around 10%, and drag due to friction will be around 90%. And if you consider example of sphere, okay, or a cylinder, so drag due to pressure drop will be due to pressure drag will be around 90%, and frictional drag will be around 10%. And if you take a body which is having a flat surface exposed to the, or flat surface in the field of flow, okay, Pressure drag will be around 100% and this will be around 0%. Okay. So this is how contributions of dP and dEF changes to the total drag depending on the shape of the body. So how do you calculate the total drag? What is the general expression for total drag? So in general, drag D is expressed as using this equation. That is D is equal to CD into A into rho U square by 2. What is this? What is the number of, let's say this is equation 2 and this becomes equation 3. So here A is the projected area of the body. A is projected area of the body on the plane vertical to the direction of uniform flow. And CD is a non-dimensionless number called drag coefficient. Non-dimensional number called the drag coefficient. Okay, so this is how you represent. And drag coefficient has to be determined experimentally. And let's see how the drag coefficient varies for different bodies. So let's take a cylinder and let's say that flow is along the length of the cylinder. So if the cylinder is placed in this way and dimensions also plays an important role here. So in this case, let's say if L by D ratio is equal to 1, that means the length and diameter of this cylinder are equal. In that case, CD will be around 0.91, and if L by D is around 2, that means length is twice that of diameter. In that case, CD decreases to 0.85. And if this L by D ratio is around 7, that means length is 7 times more than diameter. In that case, CD is around 0.99. Okay. In all these cases, the area of datum area will be pi by 4 d square. That is the area exposed to the flow. But if the cylinder is placed in this direction, that is if the circumference is exposed to the flow. Okay. So again, L by D if it is 1, let's take 2 to 3 examples. If L by D is equal to 1, 2, 5, and 40. So in that case, the datum area is exposure will be equal to DL, that is diameter into length. So if L by D is equal to 1, then CD, that is drag coefficient will be 0.63. And if L by D is 2, Then CD will become 0.68, and for L by D ratio of 5, this becomes 0.74, and L by D of 40, it will be around 0.98. And if this L by D if L by D becomes infinite, okay, that means it is having a very large length. Like diameter is minimal when compared to the length of the cylinder. In that case, CD becomes 1.2. Okay, and let's say if we have a board which is placed in the field of oblong board placed in the field of placed at the right angles to the flow. So in that case, if length and breadth are in the ratios of 1 to 10, 18, and infinite, that means length is very high when compared to diameter or breadth. Let's see how this changes. In this case, it will be AB, that is length into breadth. So if AB is A by B is 1, that is length to breadth ratio is 1, CD will be 1.12, and if it is 2, it will be 1.15. If it is 10, it will be 1.29. If it is 18, it will be 1.4. And if the L by D is, sorry, A by B is infinite, it will be 2.01. Okay. So let's see drag acting on a cylinder. If we consider ideal fluid, it is also called Lombard paradox. So let's consider a cylinder in the flow of a fluid. This is the top view of the cylinder. Okay. So again, there will be force acting in the perpendicular direction, right? So let's say this is the radius R, and here there is and this is velocity U, velocity of the flow stream, that is U, and this is P infinite. Okay. This is going to be the top view. So let's consider the cylinder in a non-viscous ideal liquid, non-viscous ideal fluid. Okay. The flow around the cylinder placed at a right angles to the flow, that is flow having velocity u of an ideal fluid. So that is the case. And V naught is the tangential velocity at the given point on the cylinder, which is given by 2u sine theta. Let's say this is equation number 4. So let's apply Bernoulli's equation and substitute the pressure of the parallel flow as P infinite. That is at location A. Let's substitute as P infinite, and the pressure at this location, that is on the surface of the cylinder, let's say that is P. So if you substitute them, uh, as we did in the previous equation when we were calculating the equation for P naught, so we were substituting all the terms, right? So it will be at the same height. So there will be no potential difference. So the potential term gets cancelled out and we'll be left with P infinite plus rho u square by 2 will be equal to P plus rho v naught v theta square by 2. Okay, so if you bring pressure terms to one side, it will become P minus P infinite is equal to rho into u square minus v naught square v theta square by 2. Okay, so if you substitute value for v naught, that is 2u sin theta, this becomes rho u square by 2 into 1 minus 4 sin square theta. Okay, so P minus P infinite by rho u square by 2 will be equal to 1 minus 4 sine square theta. That's the equation number 5. Okay. So this pressure distribution is shown using a graph. Okay. I, let me just draw how it looks. This was already shown during the class, right? So I'll just draw how it looks. So this is A, this is C, and this is B. So this is for ideal fluid. And theta varies from 0 to 180 degrees. So this is how the graph looks between the right hand, left hand term and the theta. So if you draw a graph between P minus P naught by rho u square by 2 and theta, this is how it looks for ideal fluid. This is how it looks, and this is for so let me just write it down. Laminar separation point. Okay. So this is for different conditions. So A is for Reynolds number between 1.1 to 10 power 5, and B if Reynolds number is 6.7 into 10 power 5, and C is if Reynolds number is 8.4 into 10 power 6. Okay. So these are the pressure distribution graph looks like. So it is a having a bit of right and left symmetry. The center line at right angles to the flow. So that is why if you integrate this equation, so you'll be getting pressure distribution as 0 because of the symmetry, left and right symmetry. So that is there will be no force acting on the cylinder. So this is contrary to the actual flow. When we are having a real fluid, it will be contrary because the resultant force will not be zero. But as we are using ideal flow, this is a contrary to that of a real situation, and that is what is called a paradox. Okay. Okay. So this is what is called paradox. Okay. So let's see how lift works. Let's also develop equation for lift. Same thing, we'll consider a body and we'll consider a small surface area which is having area of dA and the pressure force acting is will be d P into dA, and this will be the frictional force. This is the flow which is coming in this direction of uniform velocity. So total surface area will be A. So the lift LP, which is again we have again two forces, that is LP and LF. One is because of the pressure, another is because of the friction. Same thing, we'll be integrating both the components over the entire surface and we'll be getting pressure lift and friction lift. So LP is, same thing, like we were doing it in drag, right? Same thing we'll be doing it, and we'll be integrating over the entire surface. And LF is a similar integration. So here L, we have two components, right? That is LP, which is integral over the entire body, PdA sine theta, and LF will be integral over the entire body, tau dA cos theta. Okay. So same thing, the lift on the body is a sum of pressure lift and friction lift, which like whose proportions vary with the shape of the body. The contributions of LF and LP changes according to the shape of the body. for low Reynolds number. So that is in case if RE is less than 1. So let's see how drag varies in this condition. Just a second, the meeting got disconnected. I think I'm audible, right? Am I audible? And is the screen visible? Okay. So coming to this drag for a cylinder in case of Reynolds number and the fluid is a viscous liquid. So let me first draw the diagram. So U is the uniform velocity of the fluid stream, and this is the radius, making a theta angle. This is the pressure force, and this will be the V naught. So in case of a viscous fluid, behind the cylinder for a very low Reynolds number, that is RE less than 1. So what is the formula for RE? U into D by gamma is dynamic viscosity. So the streamlines comes together symmetrically as at the front of this cylinder. So when the Reynolds number is very low, there will not be too much eddies that are being formed here. Okay, so there won't be any eddies forming here, and the streamline flows will be coming symmetrically in the same symmetrically in the same symmetrically together with as seen in the front part. Okay, so they'll be coming to the they'll be coming together symmetrically. Okay, so there won't be any eddies forming at the back of this cylinder. Okay, but let's say if we increase Reynolds number a bit higher, so instead of 1, if we increase the Reynolds number, let's say between 2 to 30, so let's see how it changes. So that is for RE between 2 to 30. So if we slightly increase the Reynolds number from 1, that is from below 1 to 2 to 30. So the boundary separates symmetrically at the position A, and two eddies are formed rotating in the opposite directions behind the cylinder. Okay, so let me just show you quickly. So this is how it looks, and you can also see that there are two eddies which are being formed at the back, but they're in the opposite direction. Okay, but apart from this, the main streamline they'll be again coming together as seen in the front part. So they'll be coming together in the back part as well. But let's say if we further increase the Reynolds number from, or let's increase it from 30 to 40 and 70. Let's say you can have any number between 42 and 7, 40 to 70. Let's see how this changes again. So if we change Re to 40 and 70, so the eddies will elongate. Okay, then there will be oscillation of periodic oscillation of wake is resulted, and these two eddies are also called as twin vortices. So it will be almost same, but there will be a bit elongation. So let's say if this is the body, so this will be a bit elongated, and these are called twin vortices. Okay, and if you further increase it like beyond 90, so let's see how this changes again. So eddies will be formed continuously, and there will be the formation of eddies will increase if you go beyond 90. If you increase Reynolds number beyond 90, eddies are continuously shed alternately from two sides of the cylinder. And if you go beyond this, like if you go between 100 and if you take it from 100 to 10 power 5, so let's see how it changes. So obviously, if the more the number of eddies that are being formed, the drag will also be increasing on the cylinder, right? So what happens if you go beyond 100, it is from 10 square to 10 power 5, and also is between this value. The separation will occur near 80 degrees from the front stagnation point. Okay, so let's say if this is the stagnation point. So at 80 degrees, the separation will occur. That is, let's say it is somewhere around here. So from here, the separation will start happening. So this will start to separate. Okay, around this point. Okay, and you can also see clear edges that are being formed at the back. So this arrangement of vertices is also called as Kalman vertex sheet. Okay, so it looks something like this. So let's say the distance between these vertices is L, and there's one more big vertices which is separated from this pair of vertices by a distance of B. So B by L will be equal to 2.81, and this is based on Kalman's calculations. Okay, so if Re is less than R critical, that is 3.8 into 10 power 5. So in that case, this will be resulted. Okay, so carbon, you can see this carbon versus straight. Okay, sorry, if RE becomes if RE, this is the case for RE less than RC, but if RE reaches RC, in that case, boundary layer becomes turbulent. Okay, so let's see what happens if the Reynolds number is increased to RC. Okay, and let also see how the drag changes at this point. It will be completely turbulent, right? At RE, approximately 3.8 into 10 power 5. The boundary layer becomes turbulent that we already discussed. So, but turbulent layer becomes, sorry, boundary layer becomes turbulent, and the separation position is moved further downstream, that is nearly to 130 degrees from the separation stagnation point. So let's say this is the stagnation point. That is the place at where the velocity of fluid becomes zero. So now instead of 80, the stagnation point is moved to 130. Okay. So you can also see turbulent vortices that are being formed. Yeah. So for the rear half of the cylinder, just like the case of divergent pipe, the flow gradually decelerates with the velocity gradient reaching zero. And this point is called separation point where downward stream flow gets reversals and also develops eddies. The fluid particles in and around the boundary layer mix with each other by mixing action of the turbulent flow. So as the turbulent nature of the fluid increases because of high Reynolds number, there will be mixing as well. Okay, rapid mixing because of this turbulent action. And also there is a formula to calculate the frequency of vortices because the this is not going to be a continuous thing, right? So it will be taking some time to form, right? Or these vortices that will be formed after regular intervals of time in the flow. Okay, so how do you calculate this frequency of vortices or the number of vortices that are being formed? So we have a formula for calculating this. The number of vortices separating from the body every second for a Reynolds number between 250 to 2 into 10 power 5 can be obtained by at this condition the number of vortices separating from the body every second can be obtained by. So this is the formula for calculating number of vortices. 0.198 into U by D into 1 minus 19.7 by RE. So this is equation number 7. So let's try to solve a problem. So let's say, let me write down the question first. A 2 mm dia wire stands erect in air. So this is basically a cylinder. Okay. So it starts vibrating with a velocity of 90 km per hour when the temperature of air was 20 degrees centigrade. Find the number of vertices separating from the wire every second. So density of air is given at 20 degrees centigrade, that is 0.00125 gram per cc, and kinematic viscosity is given as zero point 0.1 Stokes, 0.15 Stokes. So simple, we just have to calculate Reynolds number and see if Reynolds number falls between 250 and 2 in 10 power 5. So let's calculate Reynolds number, that is U D. What is the formula for Reynolds number? By mu. So just substitute the values, and this should be around 3.3 into 10 power 3. Just solve, substitute the values and solve for it, and it will be around 3.3 into 10 power 3. So this is in the range of given Reynolds numbers, right? 250 and 2 in 10 power 5. So we can apply this equation. So number of vertices n will be equal to 0.198 into u by d into 1 minus 19.7 by re. So re we have, u is also given and d is also given. So just substitute them and you should be getting 2460 as the answer. 2460 cycles per second. Okay. So most of the contribution to produce drag is due to the separation of the stream or streamline behind the body, which develops vortices and also lowers its pressure. So therefore, in order to reduce the drag, it suffices to make the body into a shape from which the flow does not separate. Okay, so this is called streamline shaping. So you just have to change the shape of the body to reduce the drag. Okay. Therefore, does not separate. And this is called streamline shape. Okay. Next comes drag of a sphere. So again, first let's start from a lower Reynolds number. So a lower Reynolds number is less than zero point 0.2. So that is also called a slow flow, right? Slow flow around a sphere. This is called Stokes flow. Slow flow, that is Reynolds number less than zero point 0.2 around a sphere. So this is only for sphere. If the flow having a Reynolds number less than zero point 0.2, if it flows around sphere, it is called Stokes flow. So from Navier-Stokes equation and continuity equation, so drag can be calculated as Navier-Stokes equation and continuity equation. We can calculate drag as d is equal to 3 pi mu ud. So this will be equal to cd into a into rho u square by 2. This is equation number 8. And here cd will be equal to 24 by re. So this is called Stokes equation. And if you slightly increase the Reynolds number from below zero point 0.2 to a range that is between zero point 0.2 and zero point 0.2 and 5. So modification of Stokes law was done by Oseen by partially taking account of the effect of initial terms, and he found that CD will be equal to 24 by RE into 1 plus 3 by 16 into RE. This is equation number 9. So also drag force D will be equal to CD into A rho U square by 2. So if you substitute CD here, D becomes, that is drag force becomes 24 by RE into 1 plus 36, 1 by 3 by 16 into RE into A into rho U square by 2. This becomes equation number 11. Okay. So there's a graph between CD and RE as well to see how CD varies with RE for flow around a sphere. Okay. So it was already shown in the class, so I'll not be going through it again. Let's try to solve a problem again on this concept. So let me write in the question first. An aeroplane, passenger, weight of 100 kg force, comes down to the ground from an aeroplane with the help of a parachute against the resistance of air. The shape of the parachute is hemisphere or hemispherical of 2-meter dia. Find the velocity of the parachute with which it comes down. So we were also given drag coefficient. So the drag coefficient CD is given as 0.5, and density of air is also given. Density of air is 0.00125 gram per cc, and viscosity of air is also given. Kinematic viscosity is given, and it's 0.15 Stokes. So how do you calculate the velocity? So first calculate the projected area. Projected area will be 5 by 4 into d square, right? So here d is given as 2 meters, so it will be 200 centimeters. That will give us 3.14 into 10 power 4 centimeter square. Okay, and d is cd into a into rho u square by 2. Okay, and fd is must be equal to the weight of the man that is falling down. So this equation, the velocity of the parachute will be equal to u is equal to. So this is given by weight of the man. Okay, so u will be equal to, if you substitute that, CD is given, projected area we just calculated, density is given, and if D is also equal to the weight of the man, so if we just substitute everything, U will be equal to 31600 centimeter per second, which is also equal to 31.6 meter per second. Okay, so let's also see drag of a flat plate. Let's say that let's say uniform flow of velocity U flows parallel to the flat plate of length L. So in that case, the boundary layer suddenly develops because of the viscosity, and the drag force can be calculated as, let's say this is a flat plate, and when the fluid is flowing with the velocity u over this flat plate, this boundary layer will be forming gradually. So this we have already discussed in the first previous class also. Okay, so drag can be calculated as integral 0 to delta rho u into capital U minus small u into dy. Okay, so equation number 12. And tau naught is given as dd by dx, which will be equal to rho into d by dx into integral 0 to delta rho u into capital U minus small u into dy. This is equation 13. Okay. So there will be different conditions for laminar boundary layer, for turbulent boundary layer, depending upon the velocity. we'll be getting different equations for CD. Okay, I'll just write down these equations. So for the case of laminar boundary layer, that is RE less than 5 into 10 power 5. I'll directly write down the equation. D will be equal to integral 0 to L tau naught into dx. So that will be 0.73 into square root of mu into rho into u cube into LB. Okay, and D will also be equal to, so therefore the friction factor CF, friction drag coefficient, will be equal to 1.46 into 1.46 by square root of RE L. Okay, and for turbulent boundary layer, tau naught will be equal to 0.029 into rho u square into V by ux, and D will be equal to 0.036 into rho u square into L by RE for 1 by 5, and CF will be equal to 0.072 RE power minus 1 by 5. And according to the experimental results, this is theoretical, and from experimental results, CF was found to be 0.074 into RE power minus 1 by 5. Okay. So there are many concepts related to develop, lift and also design of aerofoil, blade and wing as well. Regarding the stall phenomena, like whenever angle of attack, which is like popular in aerospace engineering. So, or whenever during the flight or during the, so this angle of attack is very popular in air industries. Okay, so that was also explained during the class. So I'll not be going to that part. So, what is stall angle? What is maximum lift coefficient? All these were covered in the class. Okay, so I'll go to one important concept for chemical engineering, that is cavitation. Okay, so if a section of body placed in a liquid and if the local pressure is decreased to a vapor pressure or saturation pressure of a liquid, liquid instantly boils, producing bubbles with cavities. So this can happen when liquid flows through a wall or elbows or turbine blades when the pressure becomes sufficiently low, and this one is called cavitation. Okay. So this is frequently seen in many industrial equipments like valves, turbine blades, and also centrifugal pumps as well. So let me write it down. Is decreased to the vapor pressure or saturation pressure. The liquid will instantly boil, producing bubbles with cavities. And this is called cavitation. So this happens in walls or elbows or turbine blades as well, where the pressure will be sufficiently low. Okay. It can also be seen in centrifugal pumps as well. Okay. So since the gas dissolved in liquid in proportion to the pressure, that is using Henry's law, Y will be equal to M into P, right? So, or you can say Y is proportional to pressure of the liquid. So according to Henry's law. So as the liquid pressure decreases, obviously the dissolved gas will be separated from the liquid, right? And this separated gas will be forming a bubble inside the liquid, even before the saturation pressure is reached. So when these bubbles are conveyed downstream, where pressure is very high, they are subsequently squeezed and abnormal high pressure is developed. So at this point, noise and vibrations occurs eroding the neighboring surface and leaving a small hole in the diameter, which is relatively deep. Okay, so this causes the damaging of equipments. So if you look at effects of cavitation, the blades of pump or water wheel or a propeller of a boat are sometimes destroyed because of this cavitation phenomena, and they can develop on liquid in any liquid carrying pipelines or any hydraulic devices in which contraction expansion occurs frequently, and it can also happen in as I've told you centrifugal pump and near the tips of propeller as well, hydrofoils and also torpedoes as well. So it can actually damage the propeller and also steel shaft because of this sudden high pressure regions that are being formed on ship, and also can cause pumps to cease functional properly. So cavitation phenomenon is a very dangerous phenomenon and we don't want it to happen because it will be destroying the equipments. Okay. So we'll move on to the problem session. If you have any doubts in this theory part, you can ask me. You can unmute yourself and ask me or post them in the chat box as well. If you have any doubts, you can unmute yourself and ask me or post your doubts in the chat box as well. I'll try to answer them. Okay, if we don't have any doubts, then we can move on to this problem solving session. So coming to the first question, drag force is directly proportional to A, area, B, mass density, C, density of fluid, and D, flow speed. So drag force is directly proportional to the density of fluid, right? This is option C. Second, coming to second question, the twin versus form due to the drag for a cylindrical body in case of a viscous fluid when the Reynolds number is between 2 to 30, between 40 to 70, above 90, none of the above. So when does this twin versus form? When the Reynolds number is between 40 to 70, option B. Okay. So coming to third question, bodies with a large cross-section area will have lower drag, higher drag, same drag, or no drag. So will there be any difference with the change in cross-section area? There will be change, and also bodies with larger cross-section area, they'll have higher drag. They'll experience higher drag. That is option B. Coming to fourth question, what is the dimension of drag coefficient? Newton per second, meter per second, kg per Newton, dimensionless. Drag coefficient is a dimensionless number or non-dimension number. Option D. Coming to fifth question, for a streamlined body to achieve low drag coefficient, the boundary layer must option A flow over the body, B attached to the body, move away from the body, D move parallel to the body. So for a streamlined body to achieve lower drag, the boundary line should be attached to the body, right? So if the streamline is being separated, then obviously there will be some edges that are being formed here and it will also cause drag. So if you want to reduce this, it should be attached to the body, option B. And there should be no separation of the streamline flow. So coming to the next question, to reduce the drag, it suffices to make a body into a shape from which the flow does not separate. The shape is cylindrical shape, streamline shape. So the option A is spherical shape, B is streamline shape, C cylindrical shape, and D none of the above. That is called streamline shape, right? This we already read, discussed. Option B. So according to Stokes equation, the drag coefficient. What is the formula for drag coefficient according to Stokes equation? When do you use this Stokes equation for a slow flow or a sphere, right? So in that case, CD will be equal to 24 by R, right? So coming to eighth question, Stokes equation for a sphere is valid in Reynolds region, Reynolds number range of 0.012, zero point 0.1, 0.02, 0.225, 5 to 10, 10 to 100. So that would be 0.225. So coming to ninth question, drag force on a sphere is not proportional to which of these components, which of these parameters, u square, a, 1 by rho, or rho. Drag force will be proportional to u square. It will also be proportional to area, and it will also be proportional to density, but it will not be proportional to 1 by rho, right? In option C. So coming to 10th question, cavitation is a process of liquid formation, neither vapor nor liquid formation, vapor formation, D, none of the above. So cavitation is about vapor formation. Okay. Coming to 11th question, pressure lift is generally the dash over the whole body surface of the component in the direction normal to the flow velocity. Multiplication, differentiation, integration, or subtraction. It is integration over the whole body. That is option C. Question number 12. A successful spinner always tries to follow. Stokes equation, Kuta-Joukowski equation, option B, A and B, option D, none of the above. So we'll always try to follow the Joukowski equation, Kuta-Joukowski equation, option B. And coming to 13th question, Mach number is the ratio of flow velocity past a boundary layer to the local speed of sound. Local speed of sound to the flow velocity past the boundary layer. Inertial forces to viscous forces. Viscous forces to inertial forces. So that would be option A. Flow velocity past a boundary to the local speed of sound. Coming to 14th question, due to cavitation phenomena, the life of blades decreases, increases, remains unaffected, none of the above. So cavitation will destroy the surface of the body, right? Surface of the pipe or blades, right? So because of that, it will reduce the life of blades. So that will be option A. Coming to 15th question, the lift coefficient reaches zero at a certain angle of attack alpha, which is called the zero lift angle. As the angle of attack increases from zero lift angle, the lift coefficient decreases, increases, remains unaffected, none of the above. So it is lift coefficient will increase. Option B. Okay, so coming to 16th question, the cavitation force, the cavities grow further if liquid pressure and liquid pressure and velocity are low, liquid pressure and flow velocity are high, liquid flow is large and flow velocity is low, liquid flow is low and flow velocity is large. So when the liquid pressure is very low and the flow velocity is very large, the cavity starts growing, right? Options D. So that is it. If you have any doubts, you can unmute yourself and ask me, or you can post them in the chat box as well. If not, we can end this session. Any doubts? It can be related to the problem session, or it can be related to the problems part or the theory part. Any doubts? So if there are no doubts, then we'll end this session and let's meet on next Tuesday. Thank you, everyone. Thank you for attending the session.